Hello, our project is the Smart Hybrid Bike. Our team member Kadir Durgun, Mehdi Memendov and I. Our presentation content is as shown in the slide. Our motivation for the project is not to waste time on on-campus transportation and to prevent students from getting tired due to the sloping terrain of the Davutpaşa campus. Our goal in the project is to establish a micromobility center on the Davutpaşa campus with the support of our supporter and stakeholder YTÜ Technopark. In this way, people of all ages can use the system to provide safe transportation within the campus. The scope of our project is to solve the difficulties in transportation due to the extremely sloping terrain of the Davutpaşa campus, to ensure that the instructor and students who use our bicycle can travel tirelessly with the help of the pedal assistance system, to provide the safe driving with the help of the auto braking and lidar systems on the bicycle during the riding. According to literature research, the features and price of the smart hybrid bikes available in the market are shown in the table on the slide.
Stakeholders' expectations. Yıldız Technical University students and the academic staff are the most important stakeholder of this project. You can see many of the expectations of stakeholders on this slide. You can see the technical specifications of this hybrid bike on the table. This bike will be designed considering the conditions that everyone in society can use it easy and comfortable. In this table, the maximum speed is shown as 25 km per hour. This is the maximum e-bike speed limit adopted by the laws from many countries in Europe. In this slide, you can see the assembly of technical drawings which are designed by using SolidWorks. Detailed technical drawings of the parts are available in the project report, and there is a table of components. The picture shows the general dimensions of the bike. These dimensions are calculated with considering the average height and body measurements of the people living in Turkey. Units are shown in millimeters. You can see the strength analysis results in the picture on this slide. While performing of this analysis, a 90 kg rider was assumed, and 70% of rider's weight is accepted to be disturbed on the seat, and 30% of weight on the handlebar. In the pictures on this slide, linear dynamic analysis results are shown. SolidWorks simulations were used for this analysis. These are the approximate weights of bicycle components. The total weight is expected to be about 20. For the force calculation, we assumed these extraordinary situations. 120 kg total mass, a slope of inclined road is 10%, and rider moving at 25 km per hour constant speed without pedaling. And based on this calculation, required mechanical power is about 985 watt. Torque calculation. In this slide, you can see the steps for calculating the required torque. In this calculation, the smallest gear in the sprocket is taken into account. Under extraordinary conditions, the required torque from the motor was calculated to be about 135 Nm. Chain analysis. Chain stress analysis was performed with the values and formulas seen on the slide. As a result of this analysis, it was decided to use as chain is Shimano CN5600 model.
As a result of a mechanical calculation we made, we choose the Bafang M615 brushless motor, which is the most suitable for our project and is available in the market. The technical features of the motor we have selected are shown on the slide. The most suitable motor for our project is M615 with its torque values. As a result of our calculation and analysis, the electrical power required is approximately 940 watts for getting 750 watt mechanical power. The red line in the graph is the torque and current graph. The blue dot shows the current that's occurs when the motor stops for a very short time at each gear change of the 7-speed ratio bike. There is no controller inside the motor driver to control it, but the motor controller has a microprocessor that controls motor movements and receives the feedback from the motor. We will use the hierarchy method as a result of our research to control our motor. In this way, the motor control time will not occupy our main controller. To control our three-phase motor, we will use a 6 MOSFET combination. However, since we cannot connect it directly to the STM32F04 microprocessor, so we will use the DRV8302 MOSFET driver in between. So while Raspberry Pi controls STM microprocessor, STM will control DRV. At the end, DRV will control MOSFET combination to regulate motor input. Thus, if some problem occurs, STM will send error code to the Raspberry, and Raspberry will process convenient control algorithm. In previous example, the PI control algorithm was used in the hub motor bike, but it is not suitable for us because the motor oscillates before the desired value is reached. This oscillation is also seen in the physical speed of the motor and causing mechanical problems. If our motor works with oscillation, it applies a variable force to the chain, so chain will be break. Therefore, we will use the PID control algorithm to control our motor. So, according to this control, we will reach smooth in less than a second to the desired value. In our calculation, we calculated the current required for our 48-volt motor. The battery should continuously discharge 1 ampere. In this case, we got 960 watts. We calculate average power system consumed by turning the pedal and without pedaling. As a result, we found the working time of the battery which we choose. As seen on the slide, there are two different types of the battery in the market, covered and coverless. We will cover the part of electronic system on bike, so we will choose the coverless battery type to reduce the cost.
This is a flowchart system. Below are the primary sensors. On the left are power regulators, on top are lidars. The source of motion and the automatic braking system are right. Also in the upper left corner, there is a module for communication with the server. When the security system is triggered, the client will receive an alarm signal through the LED and telephone. The principle of control program is hierarchical. The main program or kernel runs such as module separately. Such a system allows the collection of all data in one database and prevent conflicts between modules. Further using drivers, the program goes into direct contact with sensors and actuators. The main algorithm to check the status of danger is to calculate the displacement on braking apply. Initially by deriving lidar distance to delta t, we obtain vehicle velocity with respect to the bike, and by summing it with the bike speed, we get vehicle's velocity. So by calculating displacement distance, we can check if the bicycle collides with the car. For an increasing factor of safety, we added 1 meter. Here is a simulation of the front safety system. The lidar distance is a sinus function. On the left, velocity is always constant, and on the right it's a cosine function with different frequencies. Blue dots illustrate the high collision probability status, and the black dots represent the safety distance pass, which is 3 meters. The model works in the terminal and returns parameters and status. In contrast to the front safety system, the back safety system only checks if the relative velocity is negative. The gear shift assistant offers the user to shift gear when required, and due to the various pedal assistant configuration set choices, the motor actuation graphic shifts vertically, as demonstrated on the left. So it is a gear shift assistance activation point. The velocity factor varies between 1 and 2 and changes exponentially, while the gyro coefficient is a parabolic function. Due to the low values in small range, the gyro sensor's income values will be negligible. Finally, the figure below shows the cases to take action. In this graphic, torque is sinus function, inclination angle increase linearly, green dots mean shift down, and red dots shift up. While time passing, the values of gear shift range shift down. In other words, while the client rides on an inclined surface, such as hill, the assistant will offer to shift gear earlier. On the right is the terminal output. This is our communication system diagram between client, server, and bicycle. Also, we developed a website for our product, and by reading this QR code, you can access our web page and find more details. Also, we created cross-platform apps for both iOS and Android. The apps are under developing, so right now we have a demo version.
This is the working schedule planned for the project. The working process has been completed in accordance with the schedule. This slide shows the expected cost table. The total cost is estimated to be approximately $1150. This is our PBI table, starting with manufacturing of bike frame and ending with the communication and testing. These are the references which we use. Thanks for your attention.